Welcome back to The Explainer. Today we're diving into something absolutely wild. We're tackling one of the most massive, chaotic, and honestly, mathematically terrifying events in the entire cosmos, and we're going to look at a brilliant new hack that actually solves a massive astrophysics puzzle. How? By ingeniously teaming up classical and quantum computers.
So here's the big question. How do you actually simulate the heart of an exploding star? I mean, how can we possibly model the unimaginably complex, chaotic inner workings of a core collapse supernova? Because to understand the death of a star, we have to track the absolute smallest, most elusive particles inside it. And, well, mathematically speaking, that has proven to be a total nightmare.
Just to put things into perspective for a second, a core collapse supernova produces around 10 to the 53rd ergs of energy. And get this, that energy is entirely in the form of neutrinos. 10 to the 53rd. That is just a mind-boggling scale. We're talking about more energy than our own sun will produce in its entire multi-billion-year lifespan, all released in mere seconds. So, to figure out how the star actually explodes, we've got to understand how these highly energetic, incredibly densely packed neutrinos interact with each other and their environment over time.
Okay, let's take a quick look at our roadmap. First, we'll hit the supernova neutrino puzzle, then the quantum computing roadblock. Next up, qutrits, the perfect match, followed by the hybrid algorithm hack. Then we'll look at the results and error limits, and wrap up with bridging the quantum future. Let's get into it.
Section 1. The super-neutrino-neutrino puzzle.
You see, neutrinos are basically the absolute dictators of a star's death. They're the main source of energy transport, they dictate nucleosynthesis, and really, they're our sole direct probe into the core dynamics of the collapse itself. But here's the major problem. Classical computers just completely failed to simulate them. Why? Well, neutrinos have three active flavors: electron, muon, and tau. And they're constantly oscillating between these flavors in a mathematical framework known as SU3. When you try to track these three flavor interactions across a ton of particles on a standard classical computer, the matrix dimensions just scale exponentially. It's literally like trying to predict the exact flight path of a billion caffeinated bees all at once. It just gets way too big, way too fast for any classical machine to handle.
Section 2. The quantum computing roadblock.
So you might be thinking, why not just use a quantum computer? Well, right now we're in the era of NISQ devices. That stands for Noisy Intermediate Scale Quantum Devices. These current quantum computers are amazing, highly useful, but they have a bit of a fatal flaw for this specific problem. They struggle with low fidelities, around 99%, on their entangling gates. And because they're a little bit, error-prone, executing really complex continuous calculations over long periods of simulated time becomes incredibly difficult. And that's exactly why our standard quantum methods just hit a wall here. Traditional algorithms, like Trotterization, require deep circuits. Basically, you have to run a lot of sequential entangling gates just to simulate the time evolution of the system. But since NISQ devices are noisy, doing this causes those tiny 1% errors to just pile up. They compound, and ultimately, they completely ruin the simulation before you can get any meaningful data out of the whole shebang.
Section 3. Qutrits, the perfect match.
Okay, think of a standard qubit kind of like a light switch. It has two energy levels, mapping natively to SU2 math. But as we just talked about, neutrinos have three active flavors. So forcing a three-flavor problem onto a two-level qubit, it's kind of like trying to play a piano with missing keys. The math just gets blurry and way overly complicated. But enter the quotrit. A quotrit is more like a three-way dimmer switch with energy levels 0, 1, and 2. This means it maps perfectly, natively, to the SU3 framework of those three-flavor neutrinos. It's absolutely a perfect hardware match for the physics we're actually trying to simulate here.
Section 4. The hybrid algorithm hack.
Now, this is where the real magic happens. The researchers figured out how to break down the problem using a brilliant division of labor called the Dirac-Frenkel hybrid method. Step 1. This slightly erratic but super powerful quantum computer runs very short routines called Hadamard tests just to calculate the complex matrix elements. Step 2. It takes those numbers and hands them right over to a highly reliable classical computer, which can easily solve the resulting differential equations. Then, step 3, the timeline is advanced by a tiny fraction and the whole cycle just repeats.
The core philosophy of this whole hack is just brilliant in its simplicity. Use the noisy quantum computer strictly for what it excels at. Basically, they only use it where it provides a processing advantage, like calculating matrix elements of unitary operators.
By doing this, they keep the quantum circuits incredibly shallow. There's no deep, compounding Trotterization circuit to worry about. They minimize the quantum depth to dodge the noise, and just let the classical computer do the heavy lifting of advancing the clock.
Section 5. Results and error limits.
So, let's look at how this actually performed. When tracking the survival probability of an initial neutrino state over time, the hybrid algorithm matches the exact mathematical solution perfectly in the early stages. It maps those chaotic oscillations beautifully. But as the simulation runs longer and we move to later times, the signal actually starts to damp out and blur. Eventually, it does lose its accuracy.
To understand why that drift happens, we have to look at the error limits. Quantum measurements are inherently probabilistic, right? Every single time the quantum computer calculates those matrix elements, there are these tiny statistical deviations. Over many time steps, those relative matrix errors begin to pile up. This causes the alpha norm error to spike, which you can see as a major shift. And that eventually destroys the signal's accuracy completely.
So what's the fix? Well, the researchers discovered that to keep the overall alpha norm error below just 1%, those relative matrix errors from the quantum side have to stay incredibly low, under 10 to the negative third. And because this is essentially a statistical issue, the solution they found is beautifully brute force. Just run more simulations. They actually successfully achieved this level of accuracy in their QuickForge simulator by running a massive 2 million measurement shots per quantum circuit. 2 million.
Section 6. Bridging the quantum future.
So what should you actually take away from this explainer? Really, it's that this hybrid method is an incredibly pragmatic bridge. Unlike standard methods that basically demand flawless, futuristic hardware we don't have yet, this hack works today. It avoids those deep, error-prone Trotterization circuits. It mitigates that exponential classical scaling using a selective basis. And best of all, it gives us a clear path to better accuracy right now. If you want less noise, you just throw more measurement shots at it.
By finding creative ways to divide the labor between quantum and classical systems, we aren't just sitting around waiting for the computers of tomorrow. We're actively putting today's noisy hardware to work on the universe's biggest mysteries. And it leaves us with a pretty thrilling thought. If we can simulate the complex core of an exploding star using pragmatic hybrid hacks today, what secrets of the universe will we unlock tomorrow? Thanks for joining me for this explainer. Keep questioning the cosmos.